Welcome to the Materials Science lecture on age hardening of alloys. In this session, we will explore the fascinating process of age hardening and its applications in various industries. By the end of this class, you will be able to use phase diagrams and strength versus time graphs to predict the effect of temperature and time on the strength of age-hardened alloys. Let's dive into the specifics of this process. Precipitation hardening involves particles impeding dislocation motion, as seen in the LCU system. The procedure includes solution heat treatment, quenching, and aging to nucleate and grow small precipitates. This method is also applicable to other systems like CUB, CUSN, and MgAl. Strengthening occurs upon precipitation, known as aging. However, overaging can cause some softening. Let's examine the equilibrium and metastable phases involved in this process. The spacing between precipitates plays a crucial role in precipitation hardening. Hard precipitates differ from soft ones, and the coherence of the precipitates affects the material's properties. In the LCU system, heat treatment at small weight percentages of Cu leads to coherent and incoherent phases. These phases contribute to the formation of misfit dislocations, which provide strain relief around particles. Let's test your understanding of precipitation hardening. What is the most effective spacing between precipitates? What size of precipitates is most effective? How does strengthening result from dislocation motion? Here are the answers. The most effective spacing is close together, the most effective size is small, and strengthening results from impeding dislocation motion. Great job! To summarize, precipitation hardening involves hardening and strengthening by forming finely dispersed precipitates. The three-step heat treatment process includes solution treatment, quenching, and aging. This process is applicable to non-ferrous alloys like Cu, Al, T, and Mg. Let's continue testing your knowledge. What is the most effective hardness of precipitates? What is the most effective crystalline interface of precipitates and matrix? Which metals are used most often for precipitation hardening? Here are the answers. The most effective hardness is hard, the most effective crystalline interface is coherent, and precipitation hardening is used most often for nonferrous metals. Well done! You should now be able to identify alloys eligible for age hardening, explain and draw microstructures, and use phase diagrams and strength versus anneal time graphs to predict optimum conditions for age hardening alloys. Age hardening involves solution treatment, quenching, and aging. This process forms precipitates that strengthen the alloy by impeding dislocation motion. Let's review the detailed steps and examples of age-hardened materials. Remember, by the end of this class, you will be able to use phase diagrams and strength versus time graphs to predict the effect of temperature and time on the strength of age-hardened alloys. Thank you for watching. Please like, share, and subscribe to this channel. Leave a comment below the video to share what you learned and suggest topics for future exploration. This presentation contains copyrighted material used under the Fair Use Doctrine for educational, commentary, and research purposes. Links to relevant resources are provided in the video description.